Morning to all of you. In today's class, we are going to see some automatic test pattern generation for combinational circuits. And in the next 3 or 4 classes after that, it would take, I think, two is the minimum number of classes required that will to cover the sequential circuits. So today we'll just focus only on the various ATPG available for combinational circuits. Now to start with, we will start with the Roth's algorithm, which is also known as the D algorithm. Okay, but this was widely used in the industry for a long time till PODEM came. PODEM is slightly more efficient and it is much faster than the D algorithm, and then followed by PODEM, then the fan algorithm came. But more or less they all work on the same D calculus only. Okay, so the basic fundamental remains same. We can say that some additional things which is done in PODEM makes the algorithm faster, and so does fan, which makes it even faster. Okay. So before there are some terms which we need to understand. What is a prime implicant? Suppose there is an Boolean function, right? So AB plus ABC plus A dash C. Okay, if you write for AB, that is A is 1 and B is also 1. So and C could be anything. So these are the two, the bottom two. Okay, these are the min terms corresponding to that, and ABC's all three are being 1, so that is the min term here, and then A dash C is where A is 0 and then C is 1, B could be anything. So these are the two min terms. Now from this truth table, I can make 3 groupings, right? So all these 3 groupings become the prime implicants. Okay. So these are not the prime implicants. Okay, so A, B, B, C and A dash C are the prime implicants of this particular function, right? Out of which only this and this are essential prime implicants. Okay, so this is the third one, which is called as the redundant prime implicant. Okay, now this is another example. The function is not mentioned here, but then the K map is given here. So I have all this 1, which is this vertical 2, 3 and 4, which is there. They become the essential prime implicants, 4 of them, right? And then you can have one more grouping of all these 4 here like this. Okay, so that becomes the redundant prime implicant, and 1, 2, 3, 4, 5, all these 5 groupings together can be called as a prime implicant. So this is the basic definition of a prime implicant. So coming to D calculus, right? Here, like for each of these gates, okay, the D algorithm, okay, works on a modified truth table. Okay, that we saw in the last class, that obviously there are 5 additional variables which has been taken. Okay, and over and above that, okay, it slightly modifies the truth table so as to give us more flexibility in the design, right? For example, for an AND gate, okay, I have now for 1 1 I have an output 1, for all other combinations it is 0. So I make a prime implicant, for a 1 the prime implicant is AB. So I write 1 1 as 1, right? And for the 0, okay, it is a singular cover of a logic gate. The minimal set of input assignments needs to represent essential prime implicants for both output cases of 0 and 1, right? Now if I have to have an output, I can have either this or this, right? Any combination, right? Now what is this? This is just A dash. Okay, B can be anything, right? So this AND gate will be modeled as a 0x and D is 0, right? Or if I take this particular two combinations, okay, if I take this prime implicant, it is x0 becomes 0. Okay, so now in the D calculus, this is going to be taken into consideration when I have to get a 0 at the output. Okay, I will either assign 0x or x0, right? The only thing is instead of having a 4, now we just have 3, so that saves time, right? Okay, for a small gate it might appear as very marginal saving, but when you are talking in terms of thousands of gate, it does make a difference. Okay, so the collapsing of this truth table from 4 rows to 3 rows, okay, it's a benefit which we have, okay, representing it like this. Okay, similarly for an NOR gate, what we have is like there is only a 1 out here, right? So that is for 0 0. So for 0 0 I write 1, and for this 0 there are two possible prime implicants. These two zeros, which is B is equal to 1 and A can be anything, right? Here it is written DEF because from here DEF, and that is the reason it's written like this. And then I have these two zeros also, that is A is equal to 1. That is here D equal to 1, and E could be anything. So this is the collapsed truth table for the NOR gate. And similarly for the NAND gate, 1 1 would give 0. So 1 1 would give me 0, and other two combinations, that is this combination. This is B is 0 and A could be X, right? Or this combination, this top two combination, in which A is 0 and B could be anything. Okay, so those two combinations will give me 1, right? So essentially the first step what the algorithm does is it has its own truth table for every kind of gate. It's not a typical for 2 input and 4 rows of truth table. It has got a collapsed truth table, right? Then there are some more definitions about this D calculus. First is known as the Defractor. Okay, so what we do is initially you have a big circuit. Every node, okay, every net, okay, is assigned a value of x. Okay, x is not known. You are not. The algorithm has not started. So every net in the circuit is assigned some value, and you have another set of another two sets, okay, which is known as one set is known as Defractor, and the other set is known as the Defractor. Defractor consists of all the that data of the Defractor is continuously updated. Okay, initially when we start, there won't be any thing available in the Defractor. All the nets will be marked as X, and as we move forward, okay, some gates will come into Defractor and some gates will come into Defractor, and they'll keep going out of the Defractor, and they'll also be going out of the Defractor. So what is a Defractor? A Defractor is nothing but, if you see the definition, consists of all gates whose output is currently X, okay, but have one or more error signals D or D bar at the inputs. Okay, for the Roth algorithm, we saw that, right? D is also, if you remember, what does D stands for? What does D stands for? Anybody?
1/0.
Yeah, 1/0. That means if it's a fault-free operation, it is 1, and if it's if there is a fault, it is 0. Similarly, D bar stands for 0 stroke 1, right? So now if one or more of the inputs is a D, then we put this gate into Defractor. Okay, now suppose I have to first, initially everything is being assigned X, and I have to check for then from the fault list I will pick up one fault, right? Okay, yes, So this is stuck at 0 fault. Now for this stuck at 0 fault, what is the input which is to be given? So input for this stuck at 0, I'll have to give 1 out here, right? So if I give 1 here, right, and then if I have to propagate this, I'll put say 1 1 here. Okay, so the moment I give a 1 here, this becomes D. Okay, and now once this has become D, so I have not yet assigned here 1 because I have not chosen which gate to use for propagation. But since it's stuck at 0, I know I need to give 1 here. So I'll do that first. So immediately on doing that, this becomes D, and these two gates will be mapped to a Defractor grouping. Okay, so this will go under Defractor. We'll see some examples because things will be very clear then. Okay, so these are known as Defractor. So the Defractor consists of all gates whose output is currently X. Why is it currently X? Because I have given D here. I have two things has not happened. I have not decided whether I have to propagate from here or to propagate here. So that decision is still to be taken. And hence, and also even if I have decided this, I have not yet assigned the value of A. But once I decide the path and I assign this value A to be 1, then this will come out of the Defractor. Okay, so all these gates going into Defractor is a temporary issue. Okay, as the algorithm runs, they'll go into Defractor and they'll keep coming out of the Defractor also. Okay, so that is the definition of an Defractor. Now there is something known as unique Defractor. So when we keep propagating, like for this example, if it has been decided, okay, it needs to be propagated from the top, and then you assign 1 and 0 here, and then D is available here. In this case, right, and this I have not yet assigned here. So at that point of time in the algorithm, this is the only gate which is available for propagation of D. Okay, in the previous case I had an option. Okay, here there is no option, single. So this when such situation comes, it is known as unique Defractor. There is no option, but D has to go from here to here. Okay, so this is presently in the Defractor. This has come out of the Defractor because everything has been assigned here. There is no X. So then we come to know something known as Defractor. Okay, what is a Defractor is, again we do propagate D at the same time. We have to assign the inputs also variables. So we have to keep a track of that. So to keep a track of that, we have something known as a Defractor. So Defractor are all those gates whose output value is known, but not implied by its input values. Okay, so when we suppose I want D here, I want D here. So as of now, this input D has not been assigned here. So this gate will be reflected in will be put into the Defractor, and once this value is assigned here, then this will come out of the Defractor, right? So as the algorithm runs, okay, initially, right, you insert D there, some gates will come into Defractor, and then as you keep moving forward, more gates will come into the Defractor, some gates will come out of the Defractor, and some gates will keep coming into Defractor, and when you keep assign values, they will come out of the Defractor. At the end of the algorithm, there should be no more gates available in the Defractor and the Defractor. Okay, so that is the ultimate aim. Okay, this is another to keep like for example, I have put a D here, I put a 1 here, I have a D here, D0, and then because this is a NOR gate, I know 0 is to be put here, right? So that means now these are to be assigned. So this gate goes into the Defractor, okay, because I have not yet assigned the value of C and D here. So this is another example of what a Defractor gate looks like. we have something known as propagation D cube. Okay, that is a collapsed truth table entry that can be
Hello,
used. Yeah, tell me.
sir. On the last page, could you go it once?
Uh,
Actually, I have a doubt here. I mean, regarding the like we are doing playing with the combinational logic circuits,
uh,
and how we are able to assign the values with respect to the ABCD. Like suppose at the first instance I have assigned value to the AB.
mm.
Why I want to put a kind of a delay to assign value to the CDs in here?
Yeah, could you? I just missed out your question. Could you just repeat it?
No, I mean, we are playing with the combinational logics here, right?
Yes.
And suppose at the same moment we will assign all ABCD values.
Mm,
But here, what we are trying to suppose is suppose I'm assigning the values to the AB,
mm.
I have to wait, or like we are keeping our one and get to the J frontier and then assigning value later on.
Yes.
Do we have to keep this delay here?
Yes, we will no, because we as of now we are not sure what is the requirement here, right? First, the fault site will be activated, okay, and false site, okay, has been activated, and that fault will be slowly pushed till it is available at the primary output, okay, and then from the primary output, okay, then there will be certain gates as we keep pushing no, that from D from here to here, here to here, we temporarily assign this as a 0 here, right? Here then we don't take a call immediately to assign this. So in our first run, the aim will be to push the fault, okay, a D or D bar corresponding to that fault side to the primary output, and then we do the reverse run from there to get back to the primary inputs, right? I have 2 or 3 examples, and once I think I will discuss the examples soon after another next 2 slides, then things would be clear. Okay.
Okay, sir. Thank you.
Right. So when we are propagating the faults in an AND gate, okay, if I give input, one input as D, one as other input as 1, the output would be a D. Okay, so this is the this is understood, right? So they won't. There is no. If one of the inputs is D bar, right? Correct. So if this is 1, right, and D is 1 stroke 0. So 1 0 will give me 1, and 0 1 will give me 0. So if this is D, so I get an D here, right? So similarly, if it is D bar, this 1 becomes 0, this 0 becomes 1. So this becomes 0 and 1. So this is how it works, right? And also there could be some cases where there might we might encounter a situation where for an AND gate both are D. Okay, in that case we get an output D, or both are D bar, we get an output D bar. Okay, so these are the some of the additional. First we just talked about only the binary collapsed condition here, truth table, but about over and above that, okay, the truth table will have these information also for these gates, okay, because D also is a variable as of now, right, for us. So for an OR gate also it is going to be D, and OR of D and 0 will be D, OR of D bar and 0 will be D bar, OR of DD will be D, D bar D will be okay, and for a NOR gate, if it is an 0 and D, it is an OR will give me D, but since it's a NOR, this D will get as D bar. Okay, so D bar 0 will give. So, but if I give a 1 here, then the output will be masked. Okay, if one of the inputs is 1 for a NOR gate, okay, so output would go to 0. Okay, so the data will be lost there in that case. That's not used for propagation. Similarly, for a NAND gate, it is an D1, it is an AND followed by an inverter, so that this becomes D bar. D bar will become again, if I try to put a 0 here as one of the inputs, then the output will get masked to 1. Okay, so that is not used for propagation. Okay, although that combination is there, that truth table data is available with the algorithm, but we are not going to use that particular combination for propagation of D. Okay, so these are the combinations which we are going to use for propagating D. Okay, so our aim is to propagate D to the output. Okay, now also so the starting point is this. Okay, like for each fault, right, for each fault on a gate, okay, you should have something known as a primitive D cube of failure. Okay, for example, and output stuck at 1, the primitive cube of failure, D cube of failure is 1 1 and D, right, for AND gate. If I give for each fault corresponding to each gate, okay, you will have a PCDF stuck at 0, so I have to give 1 1, right. So for a AND gate stuck at 0 at the output, for the input it will be again, if it is here or here it will be. So this is the PCDF 1 1 and D is the output. Okay, similarly for an OR gate, if the output is stuck at 0, what would be the PCDF? Can anybody say? For an OR gate, output is stuck at 0, right? So we need to force a 1. So what could be the PCDF?
X0 and D.
X0 and D, is it?
Or 0xD.
No, it's an OR gate. Okay. Stuck at 0 means I need to push a 1 here. So should it be 1xD or correct, or x1D? Right? Okay. Similarly, for an stuck at 1 at PCDF, okay. So I have to put in 0 outs. So there is no option. So 0 0 D bar it would be, right. Why it's D bar? Because if there is no fault, it is 0, and if there is a fault, it is 1. So this becomes D bar out here. So this is again what we discussed. So for an AND gate, finally this is the truth table, which is the calculus is going to use this truth table. Okay. So X stands for unknown. 0 0 is 0. Okay. 0 1 is 0. Right. So 0 with any combination will give 0 essentially. 1 with any combination, okay, will just pass this whatever it is. Okay, 1 means 0 will be passed, 1 will be passed as it is, X will be passed, D will be passed, D bar will be passed. Okay, and if it is X, one of the inputs is X, then if it is a 0, it is going to be 0. For all other cases, it will be unknown. D again, like if it is 1, it gets passed as it is. If it is unknown, then we can't be sure whether it is D, because if it is 0, then the output goes to 0. If it is 1, then it is D. So we put it as an X. It is a D gives me D. A D bar D gives me 0. Okay. So again, D bar is complementary of this, right? For if there is a 0 here, I will go to get a 0 here. D bar and 1, D bar gets passed as it is. D bar X is X. D bar D is 0. D bar will give me a D bar. Okay. So you could make similar truth tables for all these things. And then we need to, that is only when we are going forward, we need to keep coming back also, okay, in the algorithm. And while coming back also, if it is a 0, this is known as backward implication. If there is a 0 required, right, at the output of a NAND gate, so it is implied that both the inputs have to be 1. Okay, and similarly for a NOR gate, if D bar is required at the output, then we will require a D here and a 0 here, right. Now similarly, if there is a 0 is required here, then you could either have, right, a 0 or 1 here, or 1 or 0 here. There are two possible combinations, right. So this says if this is fixed, then this becomes D. If D bar is required, so if 1 is fixed, then 0 will be required here. So these are known as backward implications. So for each gate, you should know how forward implication would happen and what the backward implication would happen. Right. So what is the procedure now? Now how does the algorithm work? Okay, it first is pick the fault from the fault table. So you have so many faults in the fault table. One of them will be picked. Okay, and we select the required PDCF for that fault. Okay, and then first we do the D drive. Okay, D drive is nothing but we'll propagate the fault. Okay, towards the output. And as we keep propagating, we'll keep including the gates in the defractor. Okay, that's known as forward implication. And once it is done, and then we propagate it back, okay, to the primary inputs. And if there is some inconsistency, okay, if there is any clash of inputs, then we backtrack and choose an alternative path. Okay. So this might appear vague at this point of time, but let me explain you through one example, then things will be clear. Okay. Now suppose this is the initial state. Okay, the circuit. It's all X. Okay. So first thing I am going to do is I am going to assign X. So what the algorithm is going to do is for each net. Okay, for each net. It is assigning value xxx. Okay, it is all x. Okay, so that is at a t minus 0, so that is not shown here. All are x, right? And if I have to have an stuck at 0 here, okay, I need to assign a equal to 1, b equal to 1, right? This particular net, okay, is defined as G1 here. You can give some other name also, C, D, E, F. Okay. Just because I have already named the gates, I have used the same names out here. Okay, so G1 here indicates this particular wire. Okay, this is not a gate here, whereas here it means gate. Okay, here, right? So now for this particular gate, the first step, the first step is stuck at 0 needs to be activated out here. So I put a 1 1 out here, and the rest of all are as of now unknown. So D comes here, right? So that is the first. Now the moment D comes here, okay, in the defractor, okay, G3 gate will I'll in the G3 gate will be included into the defractor. What is the definition of defractor? If I go back, right, any gate which has got any gate whose current output is X but has one or more input signals as D, right? So that is the condition here, right? Here G1 has been activated. Now D is available here, so G3 goes into the defractor. Just move this slightly. Okay, so is the first line clear? I have placed a G3 under defractor. Is it okay? What we have done in the first line? Okay. Now
Yes, sir.
we need to do an forward implication, right? Now from D is available here, right? I need to bring D here, right? Forward implication. So I need to put in a this is an OR gate, right? So if I have to push this D out here, what is the input I need to give here?
0.
0, right?
0.
So I put that 0 here. Okay, that is known as forward implication, right? we know for an OR gate to push D here, I need to put a 0 here. So that is a forward implication action. So in the next step, I put G2 is equal to 0 here. So all this, there is a matrix will be maintained by the processor in the memory cell. Each one bit memory space for each of the nets will be created, and as they keep moving forward, this information will be updated. So now I put a 0 corresponding to this, okay, a G2. I hope it is not confusing. This G2 means this particular net, okay. I have not given another name just to otherwise it would become too clumsy with so many variables, okay. So that's the only reason I have used the same gate name out here. So I put a 0 out here, okay, and that brings this D, pushes from the D from this point to this point, and now G3 has become D, okay. Now by one forward implication, also this the J frontier and the D frontier gets modified. Now initially I had G3 as an in the D frontier, and now it is resolved already. D is brought at the output. The output is defined as D in this case. So this moves away from the this goes away from the D frontier G3, but it introduces two new gates, G5 and G6, okay, into the D frontier. Okay, so now also additionally what has happened is,
Sir,
yeah.
One question.
Yeah.
Like here we have considered like one of the gate of G3 as 0. Then why C is not changed? Like still it is X. C should be 1, no?
No, we first finish with the forward implication, and then the algorithm comes back.
Okay.
Okay, and then the that's how this D algorithm works. And it does one task at a time. Okay, it keeps moving forward, right?
Okay.
So we do that. So now there is a first what this algorithm does is it's pushes D to the one of the outputs available. Okay, so again now here I need to make it. So now also what has happened is here. Since I have put a 0 here, and for G2 this C is not defined, right, like Alhambra. So I need to later on go and assign it. So for the time being, I'll push that G2 into the J frontier, okay, which will indicate that, okay, I have moved from here and I have assigned here. So this gate is presently in the J frontier. That means the assignment of the input parameters is pending for that gate. So I keep it in the J frontier. Okay, that is how I keep a track of gates which needs to be assigned inputs. Okay, so this G2 gates goes into the G frontier. Okay, J frontier. Now there are, yeah.
For anything, any gate to be eligible for J frontier. So condition is any one input can be unknown, or
yeah,
both input
no. Any one input is unknown. Okay.
Okay.
That means if it is in J frontier, that means we need to assign. We can't leave it like that at the end of the algorithm. Temporarily, we are just pushing it into J frontier because now we are focusing in pushing the D out to the primary output. But later on, we need to revisit that and clear the J frontier.
Okay.
Right, so that is what. So now, first aim is to finish all the D frontier thing.
Hello.
Yeah. Tell me, Naresh.
Yeah, actually, sir, we just have told that like anything which is unknown to us will be coming in the J frontier.
Yes.
But I think that should not be the case. Then like G4 also would have come in the J frontier, but we are like tracking in the forward direction, right?
No. J frontier, the definition is the output is fixed. It comes.
Okay, got it. Yes.
Right? To keep a like whose output value is known. Okay, so that is why, right? So now since while we are propagating, we have fixed the value of the output this gate, and hence that has moved into till this time this was not fixed, that doesn't come into the J frontier. Okay, so So because there may be a possibility that we may not want to assign anything at all to here, as is the case here. We'll see. Okay. So this does the minimum gates which comes in the path only. We need to assign values to them. Okay. So now this is done. We were here forward G5 and G6 both we put it into the Defractor, and G2 we put it into the Defractor. Okay. So first we need to kill the Defractor. Now there are two paths. Okay. Now this algorithm randomly picks up one. Okay. It doesn't give any priority to G5 or G6. So any one it would choose. Okay. Now in this case, suppose it is choosing G5, right? So now if it does G5, then obviously what has to be, this has to be 0.
Yes,
right?
sir.
G4. So now that both G5 and G6 are removed here from the Defractor, because we have chosen one path, right? So we remove this. Okay, but all this information is not overwritten. Okay, it is written in the next row of the memory. Okay, this because many a times what happens is, if we made a decision of going ahead with G5, and if we encounter some problem later on, we might want to come back to this state. Okay, so we again don't start with 0 0. So all this information, okay, say this is what 1 2 3 4, say 10-bit register. So these are all written in subsequent memory locations. Okay, so that whenever we want to jump back to this, wherever we made a decision, if we have to come back to it, this information should be again available to us. Okay, so it is not overwritten. Okay, it is all written in subsequent lines. Okay, now here this decision was made to write it in G5.
Sir,
Right? Yeah, tell me.
sir, in third row, G4 output should be 0, na?
In the third here.
Huh?
Yeah, correct.
Yes,
So
sir.
now we need to make a decision here. So we need to put a 0 there, correct? And G5 will be. Yeah, thank you. So this G4 has to be 0, right? Now putting an 0 there puts G4 also into the Defractor. Okay. Now and the output is available here. Okay. Now that front implication thing is over. Now I go back trying to justify, trying to find out, remove these two from the Defractor. First I take about G4. Now for G4 I can assign 1 and no, I wanted 0 right there. So I can put in for G4 for E and F, right? For E and F I can take this combination of 0x, right? That is good enough, or x0, whatever. So this G4 goes out of the Defractor. Then I have one G2 which is pending in the Defractor, right? And at G2 what was required, 0 was required, right? And B is already 1, so I need to put C also 1. So this is done. Okay, so this is how the algorithm works. Okay, so you require this much of memory space is required. So one by one it will keep, and this memory is to be saved. Okay, at a, it's not so it is a memory consuming thing, because each memory, I'll give you one more example where we'll have to jump back again and do some corrections. Okay, so there is this is not a very there is
So
yeah, tell me.
in fifth row, G4 should be 0 now.
Yeah, sorry, since that mistake was there, this has come back to 0.
Hello, sir.
Yeah, tell me.
This PCD of G1 is there in the line 1, right? So because A and B both are 1 and the output is D. That's why we have written PCDF.
Yes.
But it is in all the lines. So how we are ignoring this PCDF, or
No, that is
for G1 it is always 1 1 and D, right?
so G1 is always 1 1 and D only, right? No, once it is
Yes. So
done,
this piece.
once it is done, you don't have to bother about it, right? This shows the no, no, actually we have to monitor the J frontier. There should not be anything pending here,
Okay.
right? Okay. So now obviously if you see here, it is not very efficient because we didn't choose a path. We should have chosen a path G6. Right, so it would have got one step. It would have been slightly faster because straight away we could have assigned h is equal to 1. Correct. So this decision making, right? So this is one drawback out here. So that this decision making is not very strong out here. It just randomly picks up one path. Okay, so that is a small drawback of this particular thing.
Sir, in this analysis, so I mean, we are like stopping at stage 5 because I think from one of the input to output, at least one path is complete.
Yes.
So in that case, I mean, do we have to add like condition for G6 also in this? Or once we are done from one input to output, it's done?
No, it's done. Right? What is our overall aim? That this stuck-at fault should be seen here at one of the primary outputs.
Okay.
Right? Yeah, and that is the reason why this J frontier helps. Okay, like somebody wanted to know, right? Why have we defined J frontier like that? Because this is also unknown, right? And so so only those things which are coming in the path, and we will like H and F. Okay, here for this particular case, H is not coming in that path itself. So there is no point wasting our time and resources in trying to assign some value to that particular this. Okay, had we chosen G6 here, then this G4 never comes into the picture at all, right? So that is how this algorithm works. Only while we are moving forward, only those gates which are actually going to propagate my fault will keep coming into the D frontier, and to enable that propagation, whatever is on the required gates, they will keep coming into the J frontier, and accordingly we assign the inputs. Okay, so this is how this algorithm works.
Sir.
Yeah.
Can you please explain what's the difference between D and unique D? That is not clear.
No. For example, here. After the first, I have an option to select an G5 and G6. Okay, right? G5 and G6, right? So here, okay, they are not unique. Whereas here G3 is a unique thing because now there is no option for us available, right? G3 is the unique one only. So we have, so whenever we are making a choice, it's not unique, right? Here there is no option, but this has to go through this place. So G3 is unique, whereas G5 and G6 are not unique.
Okay.
Okay. This is nothing. This was just a summary of finally what would be the values. I think this got something got shifted. Okay. I placed the final values. That's all. Okay. So finally, these are the input vectors, and this would be the state. Okay. So from your examination point of view, okay, what would be required is if something is given like this. This problem is say, let me go back this slide. If this is given, each of these nets, okay. Now, after running the D algorithm, what would be the final value of each of these nets? Okay, you should be able to write that in the text, in the provided text box itself, right? Since we are going to have an exam in an or type only mode. No, if some stuck-at fault is given here, you will do these calculations on your piece of paper, and finally, what is the final value for each of these nets? Okay, final value is this one, right? So you will write in A, this is the value, B, this is the value, C, this is the value. So that kind of thing you can type in.
So, sir, steps not required?
Steps and all won't be required because
okay.
this is going to be so final thing we need to write. Okay. Now let's take one more example out here. Okay. Now initially I have to have an stuck at one fault here, right? So if I have to have an stuck at one fault here, right? This is an NAND. This is an what is the thing which so I need to put a 0 there, right? So I have to put a 0 here, so I will put a 1 here, so that will bring a D bar at that particular state, and it will also put G5 and G6 in the differactor. Is the first row clear to all of you?
Yes, sir.
Okay. Because stuck at one fault out here, so I need to put a 0 here. 0 will give me only when 2 is 0 and also when 3 is 0. So no, 1 1. The AND will give 1 1 1 and NAND will give 1 1 will give a 0. So I put 2 and 3 1 1. So that will bring D dash. Again, remember this D dash thing, right? Okay, D dash is without any fault, it is going to be 0. If it is a fault, it is 1. Okay, and since we are talking about a stuck at one fault and we are putting an actual 0 here, we're trying to put a 0 here. So this becomes a D bar. So don't get confused with the definitions of D bar and D. Okay, so this is one, and now we need to make a choice. Okay, whether it is G5 or we need to make G6. Okay, so now let's take G5. Let's make one choice as G5, right? And now if G5, if this D has to come here, obviously 1 needs to be put as 1. Okay, so 1 here, right? So 1 has been put. So that brings a D bar out here at 9, right? So that has brought a D bar there, right? And now G8 goes into the diffractor, right? Now bringing now for this now I have D here. I have to get here outside here, right? So I need to put an 8, 10 and 11 as 1. So 8, 10 and 11 I put it as 1 here. So I get a D bar here, right? So D bar here, right? So see, when we are moving out, ultimately I need to get D or D bar at the output. It doesn't matter, right? Here I am putting D bar here. Even if I get a D at the output, doesn't matter. Okay, but what it means is, if I am getting D at the output, what it means is, when I give the test vectors, if I am getting 1, it is okay. If I am getting 0, that means it is it's a fault. D bar indicates that, okay, if it is a 0, it is fault free operation. If it is 1, it is if there is some fault. So so I am activating D bar. So not necessarily I get a D bar here. I can get D also. Okay, so don't get confused with that. Our aim is either to get D or D bar here. Okay, so D and D bar indicates D indicates that one if you are detecting 1, it is an fault free operation, and if you are detecting 0, it is it is a fault. D bar indicates the exactly opposite of that thing. Okay, so our aim is to push D or D bar to the output, right? So we came here. So now G4, G6 and G7 have been brought on to the diffractor. Now I do an back. Now I need to clear all these diffractor. So G4, okay, I need to get a 1 there. So to get a 1 there for G4, what can I do? 2, 3 are already 1. 2 is already right. So and what about 1? Okay, these are the 3 gates, right? G4, G6, G7, okay, which have come. So G4, I require a 1 here, right? So 2 is already 1, right? So I don't have an option. So I need to put a 0 here, right? So I am going to put an 0 here. Where is it? I'm going to put a 0 here, and I am removing this G4 from this list. Is this okay? I have removed G4 from the J frontier list by putting a 0 in G5. Okay. Now I have G6. Okay. G6. I need a 1 here. 4 is free as of now. Here it is D. Correct. So 4 is, so I have to put 0 at 4. So there is no option. So I put a 0 at 4, and I remove G6. And for G7, I need a 1 here, right? So I can 3 is already assigned 1 earlier itself. So that option is not available. So G7 here, okay, this was not assigned. So I put a 0 here, right? Now, because I am assigning here, this G3 is going to come into the J frontier, and G1 is going to come into the J frontier, right? Now, for G3, right, at 7, I require an 0 out here. That means if I have to have a 0 here, 4 has to be 1, and also 2 has to be a 1, but 4 is already assigned 0 here. So there is a contention here. Okay, so that cannot happen. So that means I have made a wrong so it will think, okay, where is that? What can I do? So it will go back to where I made a decision. Okay, a branching decision. So here I had chosen a G5 path, right? I could have chosen G6 path. So it will go back. Okay, again it will start from here. Right, again it will make one more run with G6. Okay, it can do that. So in most probably in this particular case, if you do reset G6, right, and then you run again, you will encounter the same problem. The third option is available is I can simultaneously take both these paths, because DD also can come here, right? DD also can come, it can go here. So it will in the third run, probably in the third run, or even in the second run also, because it is an event driven, right? So when we go in the event driven, rather than going from 0 1 selection, then going to 1 0 selection, and then coming to 1 1 selection, right? It would be a better option to make a selection of 0 1, 1 1, and 1 0, because there was 2 paths, right? This was the first selection I made. Then instead of going to this selection and this selection, 0 1, I can make a 1 1 selection and come back to 1 0 selection. Okay, 0 1 indicates a selection of G5 G6. Okay, I'm just giving just the logic behind selecting one of this path. So because here you will find, okay, lesser number of events would occur, right? So what it is going to do out here is I am choosing both the paths G5 and G6. Okay, I'm going back here. Now when I'm choosing both the paths out here, G5 and G6, right, then I am having D and D here. Okay, so I am putting this into the D frontier. Okay, G8, right? And then I am putting I am having DD at both the places. Okay, so this initially I have put 1 1 D bar here, right? And then I am going to choose both this path, and hence this is going to be 1 and this is going to be 1, right? So I am going to put I might have put 1 out here, and I might 1 out here, and then putting those two ones have brought D at 9 and 10, and that has put G8 in the D frontier, right? Now putting this coming here, now I have 8 and 11 coming into the corresponding gate is G4 and G7 coming into the J frontiers. Okay, so these are the two gates which comes into the J frontier. Now if you try to set the values for these two gates, okay, if you do an back. Now for that 8 and 9, 8 and 11 has been put to 1. Now if I have to go back, remove for G4, I can 2 is already 1, right, and this needs to be put to 0, right. So I can put that to 0. There is no issue, and this is D bar initially itself. And for G7, okay, for G7 this node needs to be put to 0 here. Now these two zeros I have put, whether it is going to be 0 or not, let's just see. It is this is G3, right. G3 I have one input as 4, one as 2, 4 and 2 are 1, so obviously it will be 0, so there is no clash. Similarly 7, no, similarly 5, this 5, so 1 is 1 out here, 3 is also 1, so there is no clash. So now this is the final answer. So there is no, so whenever there is no contention here, so this will run like this, okay. It will go find, now propagate D to the output, and then from there it will keep coming back, okay. And then it will, if it encounters any contention, then since that memory is saved, it is still there where you made a choice, it will go back there, okay. Now only thing you need to remember is not necessarily that one gate is chosen, you choose the next path, okay. It can, all the combinations are available. Now here there are only 2 gates, so there are total 3 possible combinations, one here or both. Similarly, there could be a situation where there could be multiple paths available. So all those paths will be explored one by one by the algorithm till you get a set of input out here, right. So I think there is one slide which we will which will wind off.
Sir,
Yeah.
sir, in previous slide, that ninth one, why D to 1 it changed actually? In 6th and 7th row, the ninth output, ninth column.
No, so that could be a mistake I might have.
D.
Yeah.
Okay.
They'll will continue to remain. I just tried the color scheme. What I tried to do is in that particular row where I'm making the changes, I have put it in red bold, so that subsequently when you're looking at the PDF, you have some idea about what I have done. Okay, so I've used some kind of logic which appears logic to me. I am not sure if it makes sense or not to you guys, but I tried to do that, so that later on when you are referring to the PDF, you have some idea. Okay, so this one. Now this D algorithm, okay, D calculus, okay, advantage is it will for sure, if the fault is not redundant, okay, it will check for all the possibilities. It will take time, but it will give you the output. Okay, the only reason why you may not get an output will be if there is a redundancy. Okay, in that case it will get stuck. Okay, the disadvantage out here, it takes lot of memory. Okay, so now you can imagine that we are speaking of only 7 gates, and we know so many memories is already, it's taken 8 steps. Okay, probably if it is going to take G5, it had it taken G6 first, rather than combination of these two, a few more steps will be there, right? So it is slightly slower, and it doesn't choose the best forward path. Okay, it just takes one of them and it keeps moving forward. It doesn't apply any logic. Okay, and then it goes on relies on backtracking. Okay, it says, okay, let me take one decision and go to the final thing, and later on if there is an issue which I foresee, I'll redo it. Okay, that is the kind of logic. So we talked about D algorithm. Let's see two other algorithms which are slightly better. First is known as PODEM. Here internal nodes are not assigned anything. Okay, only primary inputs are assigned. Okay, so the entire requirement of memory and the source tree reduces, and PIs are assigned in the forward implication time itself. Okay, that was, I think, that was the doubt which Alam had. So why not assign the primary input initially itself? So that is what this particular algorithm does. But then the thing is, many a times again doing this also, there will be situations where the fault doesn't get activated at the output. Okay, because you are assigning initially itself, you are assigning primary input. So there could be situations where the fault is not getting activated, or the propagation path is not proper. Then you might have to come back again to the very first stage where you are assigned the primary. So although it is much faster, but there could be some situations where this could get stuck, and unlike in the previous case, an intermediate result we are using it here. Here we go back to the primary input. Okay, we'll see an example. We'll see examples, then it will be clear. For example, for this circuit, initially if I need to do it stuck at 0 here, I assign 1 1 here. Okay, so that pushes D here. Okay, the next step is to propagate this to here. Okay, again to propagate I need to put a 0 here, right? So two things. First, I give this here in the primary input itself. During the propagation time itself, I know there is a 0 here. I will straight away assign 1 here. Okay, so I'll do that. The second thing which this does is, now I have to make a decision whether to go for G5 or G6. So initially when the net list is run, okay, for the scope analysis, right? So we know, because this is done, right? We saw that before we start with ATGP, scope is done, and only the difficult ones are the ones which we are handling now. For the easy ones, we run a random test pattern generation, and we saw multiple faults and are being detected by few algorithms which we saw in the last class. Okay, and now we are talking about specific faults and those difficult faults. So but this data for each of these nets, right, the difficulty level data or the scope analysis data is available, right, for each of these nets. Since we have done that earlier, this algorithm makes use of that to choose the easiest path. So in this case, which is the easy path? Obviously G6 is an easy path, right? So because the difficulty level here, right, is easy. So since that data is available here, so it will just assign h is equal to 1, and it will finish the algorithm in just 2 or 3 steps. Okay, so this is how PODEM works. Okay, so this is the first is you activate a fault, and then as you keep progressing further, okay, you keep assigning the primary inputs itself. Okay, and then if you encounter a problem, then you again come back and reassign the primary inputs. Okay, in this particular example, we have not encountered a problem. Okay, maybe in one more example I'll try to show where there is a problem and we'll have to reassign things like that. Okay, so in this, so there is no problem encountered, and also whenever a decision needs to be taken, so in that circumstances, what it does is it will check for the data from the scope analysis, and there whatever is the easiest path, it will make that. So this is much efficient than the D algorithm, right? Now this is another.
Sir,
Yeah.
Sir, in last case, so G3 output should be D, na?
Yes. Like I told you, this the first time I'm taking this course, so all the slides are new, there could be errors here
Yes.
and there.
Yes, sir. Yes.
Right. Okay. Finally, D would be available here also. Okay. So that is not shown here. That's okay, I guess. Okay. So this is how this works. Now this is another example, right? This is stuck at 1. Okay. Now if it is stuck at 1, I need to have an 0 here. So I need to have a 0 here. I need to have a 1 here. So I go back here, right? So I can either have an this is an XNOR. I can have 1 1 or 0 0 here. So again, I need to it doesn't keep anything in memory. It will just assume, okay, let me to get a 1 1 here. Let me take this 1 1. Okay, it will take one decision at the primary input. No information of this net is stored. Okay, I require a 1. I put a 1 1 here. Okay, now that 1 1, okay, will give me 1 here, right? Because I have a 1 here, 1 here, I have a 1 here. So this is suiting. So this chain, there is no problem in getting this 1 here, and that 1 is going to give me 0 here, right? And I am getting D bar available here. So now so that's the end of it, right? I don't have to bother about what is C and things like that, right? So sometimes what happens is, suppose this is not available out here. Let me if this is not available here, I need to suppose this gate is not there. In that case, probably I need to propagate here, right? And then I assign and then probably there is a requirement of a 0 out here, whereas I have initially assigned 1. Then it will go back again. It will start from where it has been. Can 1 0 meet this requirement or not? So this PODEM algorithm, only thing is, every time it encounters a problem, it will go back and do a different selection of the primary inputs. Okay, in these two examples, last and this examples, we have not encountered a problem, but the only thing is, whenever it encounters a problem, it will go and start from the primary inputs. Okay, that's a small disadvantage, you could say. Okay, that could be there, like for this particular example. Okay, exactly. Now suppose I want an 0 here. Okay, so I'll go back. So I have to detect an stuck at 1 here. At fault. This is the fault which I need to do. I have to detect a stuck at 1 fault at L. So now what this does is, okay, for this, so I will go and assign a 1 here, and I have to assign a 0 here, and I will assign a 0 here. Okay, and then this is the first thing this will do, and then I will go on the other path also, trying to assign the values of the primary gates. This is an 0 here, so I need an 1 here. I require an 0 out here, right? And that is not possible here, because you have already assigned a 0 here, right? Initially itself. So it will again go back. It will go back and undo this assignment. Okay, because if I put a 0 here, from the top also I'll get a 0 here, and it will mask this gate. So 0 is not the option. Then I have to go for actually a 1. Now if you see here, this is the way actually the final combination would work. If I have 0 1 1 here, then I have a 0 here, I have a 1 coming here, 0 1 will give me 1 here, and E equal to 1 here. So this is the actual comp. Now if you see just the PODEM, it would make multiple hops. Okay, right from the output to the input. Okay, it will make multiple hops and then come to this conclusion. Okay, now this is whereas the fan algorithm, which we are going to see now, it converges pretty faster. It comes out with a solution pretty faster. Okay, how does it come faster? Is what it does is, initially when the net list is given, okay, the moment even before running the algorithm, what it does is it checks for headlines. Okay, what are headlines is where it is those headlines are driven by the primary inputs, okay, and can be separated from the rest of the circuit by cutting a single line known as an headline. That means if you cut it here, right, there is no branching out here, right? So this is one cone, EF. Similarly, this J, I can cut it here, right? So this much I can't cut it here because this J is going in the bottom also, right? So H and J, this is a single cone, okay, and this is the headline. Similarly, this is a single cone, okay, and whereas this is. So what this fan algorithm does is, once you provide the net list, it will identify what are the headlines, okay, initially itself. Okay, once it identifies these headlines, for each headline, let's say for H, for 0, okay, if I have to H is equal to 0, what are the inputs? It will just assign, it will keep that in a truth table aside. So and for J equal to 0 or 1, what is the truth table? Okay, so if that is kept aside, then it will consider this thing as a single net only. Okay, so that makes the decision making pretty easy. Okay, so it simplifies the thing. So like for example, if you take this particular thing, if you are running the PODEM, if I have to 0, if I require a 0 here, it will take it will push a 1 here first, okay, and to get a 1 here, it will 0 here, and then it will assign 1 to this particular node, this particular input, and then it will come back 0 here. I want a 0 here, so I will assign the second input as 1 and a third input as a 1, right? Whereas what a fan does is, it will consider this entire thing also as an there is no branching, so it can consider this entire thing as an single, and for a 1 here, right, and I need a 0 here, so it will straight away assign 1 1 1 1 here, right? So it does some pre-computation, right, of the heads, like this is an header, this is also an header. So suppose I want a 0 here, it will straight away in one go itself, it will assign all the values here. So a fan is a small modification. It essentially works like PODEM only. Only thing is, instead of PODEM keeps assigning each variable, each input in one run, okay, single run, one input, okay, depending on what is the output required. What fan does is, for a particular headline, okay, if I want a 0 at this particular headline, it will pre-compute and keep, okay, for this particular input combination, I'll get a 0 here, because there's no branchings involved here, because if there is branchings, I cannot do that, because that branch will get may affect the other part of the circuit. Okay, so that is why the concept of headline is important, because these particular inputs can affect only this node, correct? So initially itself I can pre-assign the value. If I want a 0 here, okay, this is the particular test vector. If I want a 1 here, this is the set of test vector. Okay, so that saves a lot of time. Okay, so that is the small modification with respect to PODEM, right? So this is another example of fan, how it works. So these are the now if you see here, this is one headline, and this is also can be considered as a headline. It is independent, right? So now if you see here, if I have to have an stuck at 0 fault here, okay, so first I assign an A equal to 1 and B equal to 1. Now I have to transmit this from here to here, correct? Now in this case, right, 0 here, this is not a headline, because I have a B coming from here, so this is not independent out here, right? So that is the reason why you have to assign separately C is equal to 1, E is equal to 1, although it is written in one step, right? But PODEM does this in 2 steps, okay, these 2 things. Because it won't, because there is an input line which is common to these 2 lines. So this will be done in 2 steps, C equal to 1, C equal to 1, right? Like in the case of PODEM. And then I need to bring this to G5. Okay, now this decision is to be taken. Either it is through D needs to be propagated to G5 or and G6. Now we make a decision, it has to go through G5, right? Because or G6. So if you use the scope analysis, G6 would be better. If you don't use the scope analysis, then it can choose G5 also. If you are choosing G5, right, because I don't have to assign, it will straight away assign 1 here and X here, right, because this will be pre-computed and kept. If I want a 1 here, what is the input combination here, right? So I don't put a 1 here, compute H, again 1 here, compute J. So these 2 steps, okay, will be it is pre-computed and kept by the algorithm. So straight away it will assign whatever is the value, okay. So that is the only thing. It is just a marginal increase from the PODEM algorithm. It makes it slightly faster, because wherever headlines is there, that information is pre-computed and kept. Okay, that's the only difference. And finally we get the test vector. What is not shown here, because the focus was on fan, that it won't choose G5, it will always choose G6 gate, because this is easier, okay. So but this was just one of the examples which I picked up from one of those lecture videos. But fan wouldn't, because fan is a further modification of PODEM, further improvement to PODEM, and PODEM does the SOAP analysis, and then it would pick up a G6, okay, because it is much easier to get G6 activated than G4, okay. Unless this F itself has got if it's not a primary input and it has got some other, it's coming from some other net, then the difficulty level will be more. But if F is a primary input, then obviously transmitting it through G6 will be easier. So PODEM and fan will zero on to this, okay. So that's all for today, and in the next class we would start with the sequential testing, okay.
Sir, can we go to last slide?
Yeah.
Sir, in the last line, test generated A, B, C, E, H, J, F. So here J and F are XX. So because we are considering output through G5,
yes,
that's why we are considering F as anything.
yes,
because we are
yes, right. So in case we are considering with G6, both H and G will be X, right? So
H and J will be X.
Yes. So if a fan algorithm or a PODEM algorithm is given in the exam, please do consider the easiest path available. Okay. This is I took it up from this video lecture. The thing is, just to demonstrate that these two have been clubbed as a single input. Okay, so this is not exactly a very good example. I should have put some other example, but G6 will be the only option available.